Well, welcome everyone. So my name is Ali. I'm a general partner on the crypto team here at A16Z. And today we are all very excited to be announcing that A16Z is leading Matter Labs' Series B round. And our guests today include Alex Gluchowski, who is the founder and CEO of Matter Labs, and another Alex Vlasov, who is the head of research and development at Matter Labs. And we also have Dan Boneh, who is a research partner with us here at A16Z, and he's also a professor of computer science at Stanford. And the plan for today is for us to just discuss some of the open trends in the space of crypto and Web3, some of the open problems that the space is facing and that we need to tackle, and the way that Matter Labs is going about solving those problems and why we think it's one of the most exciting projects in the space. So maybe to start, I'll just share some context behind the space and our investment in Matter Labs and why we're so excited. And then I'll turn it over to Alex G, who can tell us about the founding story of the company. So the first thing that I'll say is that, well, for those of you who might not already be within the space and are new to Web3 and to crypto, the best way to think of a blockchain is as a new kind of computer. And the biggest misconception in crypto continues to be that crypto is really just about cryptocurrency, that Ethereum is really just the silver to Bitcoin's gold, and that it's really all about just like payments or digital gold or remittances. And all of those are interesting use cases, but they're really just the beginning, because blockchains, the best way to think of blockchains is actually to think of them as a new kind of computer. And I think if you look at the history of computation, we went from mainframes to mini computers to personal computers to mobile and cloud to now, we would argue, blockchain computing. And each of those waves of computation has introduced new capabilities that have very nicely complemented the previous waves that preceded it. And blockchains are no exception. Blockchains introduce a unique capability that allows developers and programmers who are writing code that run on blockchains that allow them to essentially build programs that make strong commitments about how that code will behave in the future. And so, for example, Bitcoin has code that makes a commitment that there will only ever be 21 million Bitcoins. And that's the best, or the simplest example, really, of what you can do with a blockchain. But there are new blockchains like Ethereum, which are fully programmable and have very expressive programming languages that allow you to do much more and allow you to build, say, programs that act as full-on decentralized social networks, where you can have a lot of the functionality that Facebook gives you, but you have no trillion-dollar monopoly in the middle to control your data or to decide like who gets to see whose posts. Or you can build crypto-enabled games where there's an entire kind of economy that's driven by cryptocurrencies and by NFTs that can scale to a far larger degree than just traditional centralized games by virtue of having the composability of crypto and of blockchains that kind of empower them. And so it's a new paradigm of computation that we see as expanding the capabilities of what we can do with software. But of course, I think you may all be able to remember that every new wave of computation at the very beginning started off looking like a toy and had all sorts of limitations that made it difficult to use at first. But with time, those things get better, and like you get like great founders entering the space to address some of those limitations. And as we've seen, like for example, like mobile phones, they've gone through an incredible arc, and now mobile phones today are kind of a very functional form of computing that just about like billions of people in the world rely on. And blockchains, again, they're no exception. We're still kind of in the early innings of blockchains as a computational paradigm. And one of the key limitations that blockchains have today has to do with performance. And as a way of making this concrete, you can think of Ethereum, which is probably the dominant blockchain computer that has the most traction today. As an example, it currently can only really process around 14 quote unquote transactions, or 14 kind of, you can think of them as computations per second. And that's really not enough in order to truly be able to scale to billions of users. And so one of the key problems in the space is to figure out how we can get blockchain computers to scale. And that's where Matter Labs enters. We're very excited about all of the work that Matter Labs is doing with zero-knowledge proofs, which are a cutting-edge primitive from cryptography that we'll talk about, and zkSync, which is one of the primary things that Matter Labs is working on, as one of the most ambitious and promising efforts towards allowing blockchains to truly scale. So that's a little bit of the context and background. And with that, I would love to turn it over to Alex G, who can tell us a little bit about kind of the story behind Matter Labs and how it all came to be.
Thank you, Ali. I'm really excited to be here and really excited to be working with you guys now. This was a great intro, a very, very good analogy. And I would like to extend it with, like for me, the blockchains, when I first learned about Bitcoin and later Ethereum, and more powerful way to interact with this kind of new computation, was also about interaction, how this computation makes interactions between people less, more seamless. And, we can compare it to internet. So the internet is also a form of computing, but it's a form of computing which is interconnected, and it leads to much more direct exchange of information. And it makes information a lot more free. So you can, see everything that is happening on the other side of the world instantly. You do not have intermediaries of this information. You can just get it from the first hands. So the same thing that the internet has done to information, I think the blockchains will do to the world of value, to the network of value. So we can exchange value directly without intermediaries, overcoming the trust issues between people without involving third parties, which might not be the most beneficial way to structure those interactions. I once learned that when the shipping containers were invented, this single invention boosted the world GDP by 5 to 10%. And I feel like blockchain crypto technology in general has the similar potential of making us a lot more accelerating the progress of humanity a lot faster. So I learned about Bitcoin in, I think, 2014. Back then, it was about payments, about sound money, about the freedom and sovereignty of your finances in the age of rising inflation. I got very excited about the economics ideas, the political side of it, because I'm coming from Ukraine. I was born in the Soviet Union. And as a kid, I survived a hyperinflation lasting for 3 years. And I could see the society deteriorate because lack of trust and these institutions being corrupted and not functioning. To me, Bitcoin was that. But I quickly realized that the idea of hyper-Bitcoinization just based on Bitcoin is kind of utopia because of a lot of usability issues and a lot of issues with just general lack of functionality which you need for a real financial system. And this all changed with Ethereum. So I got extremely excited about Ethereum. I digged into research, looked into different problems that we had there. And it was clear that scalability is one of the core problems, and it requires a breakthrough in technology to solve it. So scalability was something that must have been solved in order to bring the promise of blockchains to everyone. So we actually needed to scale it to everyone in the world. And when I learned about zero-knowledge proofs for the first time, it was clear that this is something this is something out of this world. Like this is a magic technology which is called to solve precisely this problem, and it was just extremely exciting to start working on this. So I went to different conferences, meetups, and eventually I met my co-founder Alex, who came to the same idea from a different angle. He was working on scalability on a technology called Plasma, which was popular back then as a direction of solving Ethereum scalability. And we just realized that we have to start working on this together. We built the first prototype, and we founded the company, which has the mission of enabling everyone in the world with access to affordable blockchain that preserves all the properties that make Ethereum, Bitcoin, and other decentralized, truly decentralized blockchains so valuable, namely the no single point of control, true decentralization, like true peer-to-peer nature, where everyone is equal and no one can dictate rules that other people did not voluntarily opt in before. And this is a network which is unstoppable. No matter where you live, how sane or corrupt your government is, you can absolutely rely on the math and cryptography behind blockchains and be sure that the rules will be enforced equally and fairly for everyone. And so this is what we're working on with Meta Labs.
It's a truly great story. I'm curious, do you remember the moment when you first learned of zero knowledge proofs, or was it kind of just ambient and you kind of gradually got into them?
I do remember it very well. It was a election in Berlin held by Chris, the author of Solidity. But back then, it was about zero knowledge aspect of zero knowledge proofs, which we actually paradoxically do not use in scalability. So what zero knowledge means that we can provide we can provide proofs of some computational facts, proofs of computational integrity without disclosing all the information which was used as an input of this computation. But this is not what we need. What we are interested in is succinct property of this blockchain. So we operate with a construct called SNARK, which stands for succinct non-interactive arguments of knowledge. And succinctness means that you can verify the results of this computation a lot faster than it takes you to produce these results and actually to just naively do the computation.
That is, yeah, that's exactly right. And we'll kind of dive into some of the properties of zero knowledge proofs and why they're so important in the context of blockchains. I'd love to, before we do that, I'd love to, Alex V, I'd love to get your side of the story and how you got to know Alex G and how you got into the space.
Well, most likely, first I should answer the last question as how I got to know just anything about zero knowledge. And it was actually around the time of one of the first ETH global hackathons, one which was in Waterloo, Canada. Around the same time as there was on this hackathon, there was a lecture about the first Starks with gigabyte-sized proofs. Around the same time, Vitalik was mentioning about snarks. So I just decided to Google it, and then I found a very interesting presentation. I don't know what was the source, but it was very clear how they work and very exciting for their properties. But then I decided it's more like too early to go into there, because around the same time the plasma concept was introduced, and on this hackathon we tried to do the first very simple prototype of plasma for Ethereum. And later then, just as Alex mentioned, he actually, I was on one of the plasma calls, and I've mentioned that kind of as a side research, we're trying to do some optimizations for gross 16 proof generation to be run on the GPU. Was completely aside. It was for general interest, and at this moment in time, I still consider it maybe a little bit too early. And then I get a message in Telegram from unknown contact, and it says, well, I was the person from the plasma call who mentioned working on a GPU, and are you going to the DevCon this year? And I said yes. And then Alex said, well, let's meet in there. And this is where we actually met the first time in person and decided that let's go into zero knowledge space. And even if it's going to be hard, well, we'll have to spend a little bit more time and do it with our hands. So then we started to build the corner part of the system. Some of those still live in the current zkSync 1.x, and zkSync will be part of zkSync 2.0. And this is how story begins and now continues.
That is awesome. I always love hearing the kind of the genesis story for great companies. Dan, so I think you're probably one of the world-leading experts when it comes to cryptography and zero-knowledge proofs. And I think you're also probably one of the best teachers in the world about all of this stuff. And I was hoping for our audience, if you could kind of give us an intuition for what zero-knowledge proofs are and why they're so powerful. They really do feel like magical. It feels like it should be impossible to do what you can do with a zero-knowledge proof. And I feel like conveying that to people who are listening would be awesome.
First of all, congrats, Alex G and Alex V, on everything you've built. It's really quite remarkable to see this coming to fruition and becoming reality. And thanks, Ali, for the introduction. So let's see. So snarks and ZK snarks, I totally agree with both Alexes. They're kind of magical objects. They basically let you prove that something is true with a very, very short proof that's really easy to verify. And that's kind of exactly what you want for scaling a blockchain. You can basically produce a proof that 10,000 transactions are valid. The proof is going to be very short, so it's easy to write it onto the blockchain, and it's going to be very fast to verify. So it's easy for miners to actually verify that it's true. And it's interesting that Alex V, I think you said that, or Alex G, I don't remember which one of you said it, that actually for this type of scaling, you mostly need the property of snarks called soundness. That is, that the snarks are actually cannot be forged. You cannot prove a false statement, and not so much the zero-knowledge property of snarks. So the zero-knowledge property kind of comes up in the areas of, when you're trying to prove that something is true without actually revealing anything about your data. So like confidential transactions, private payments, compliance, things like that. That's where the zero-knowledge property is needed. So both of those are supported by snarks and ZK snarks. And I have to say, it's been the last couple of years have been a wild ride, because it's been amazing to see this stuff getting deployed at such a wide scale. And what you guys are doing is literally going to enable millions of people to transact at a much higher rate and much lower gas fees using the beautiful math of snarks. And it's really quite a beautiful math that goes into these things. I have a million of questions for you, so I'm really excited to get to the point where I can ask you questions. So I'll stop there.
No, that's great, Dan. I think one of the intuitions that has helped me in the past is that if you think about what a blockchain is and what a blockchain needs to do, is that it needs to essentially enable its participants, and in the case of something like Ethereum, these are the validators or the miners who are processing all of the computation that happens on the blockchain, to verify that the computation is correct. And the way that happens now is that every miner, every validator, has to basically do all of the work, has to essentially run every instruction of every computation that runs on the blockchain to convince themselves that the computation is correct. And that's very inefficient, because you've got, say, 20,000 validators. Each one of those 20,000 validators has to do all of the work, every instruction, every computation. There's a lot of redundancy as a result. And the beauty of a zero-knowledge proof is that instead of having that model, you could have a single validator do the work of computing something that's expensive to compute, and then producing a zero-knowledge proof that everyone else can verify very, very cheaply without having to do all of the work. And that was kind of like one of the intuitions that helped me understand why this technology is so powerful and so well suited for blockchains. And I think I agree with Alex about how the key properties here initially for scalability are the soundness aspect and then the succinctness aspect, the fact that you can actually have these things exist on a blockchain because of the fact that they're so compact, make them like a perfect primitive for this space. So with that kind of introduction about the technology, Alex G, would love to dive into the roadmap and some of the stuff that you guys are building. So I think recently you launched a testnet for your ZK EVM, and curious if you can walk us through what exists today and what the roadmap is for things to come.
It will be helpful to begin with a short story of the product, what we released in the past. The protocol that we've been developing from the start is called zkSync, and we have the first version of the protocol, the MVP, released more than a year ago, the summer last year, and it was a ZK Rollup that enabled much faster payments on Ethereum, or like much more affordable payments. It is live. We have processed over 4 million transactions. We have lots of integrations, lots of protocols, wallets, dApps supported. It's been broadly used in the ecosystem. Almost all the Gitcoin grant rounds have been run on zkSync, with 99% of transactions going through zkSync rather than on mainnet. But it had a very limited functionality. And in fact, many people believed, including Vitalik Buterin and leading cryptographers, that making zero-knowledge rollups generic, making this blockchain scalability protocol generic and being able to execute arbitrary contracts will take a very long time. But luckily, we had a couple of breakthroughs in purely engineering techniques and in some heuristics, how we apply zero-knowledge proofs to provide this blockchain scalability specifically, that enabled us to make a generic programmable ZK rollup already this year, and actually make it as far as close to full EVM compatibility. And this is what we're extremely excited about. This version is called zkSync version 2.0. And yeah, indeed, we have a test net. We just launched our first fully ported EVM dApp last week on it. It's the port of Uniswap version 2, which contains the Solidity smart contracts, the front-end part, which interacts with Web3 RPC APIs in the same way, essentially, that how this application works on mainnet. So the next step for us is to open this testnet to the general public, make sure that it's running in a robust and stable way, and then bring it to the mainnet.
And zkSync is essentially an implementation of what people know of as a ZK Rollup. Do you want to describe for everyone what a ZK Rollup is and what its relationship to Ethereum is, and the fact that it's a layer 2 and how the two kind of interact, and kind of how to think about it from a 10,000-foot view?
So ZK Rollup is a scaling protocol from the Rollup family. The rollups are a continuation of Plasma. So this is an idea that you can take a lot of transactions, put them in a block off-chain, compute the result of that block, compute the cryptographic commitment to that block, which is a Merkle. We use Merkle trees for representing the state. So we use the Merkle root of this tree, and we store it on the contract, on a single contract on the mainnet, which contains all the value. So the value doesn't move hands on the blockchain itself. Instead, you just record a very short hash, which represents the commitment to who owns what. This is very similar to the Rice stones, which remained. It's a very interesting analog, and I recommend to look it up. The stones used as money on some Pacific island that remained in place, and they only changed the title of who owns them. So this is what happens actually in a rollup. So the interesting thing about rollups in general is that we still publish the data for all transactions, for all modifications of the state through the Ethereum network. So we do not use Ethereum storage, but we make sure that all the data is available to all the listeners, so all the full nodes. So anybody can reconstruct its state, and together with zero-knowledge proofs that ensure the validity of transactions, that make sure that no one can run an invalid transaction, violate the rules of the smart contracts, which we use there, spend or forge on additional money. These two properties together give you security, which is derived from the mainnet itself. So in the rollup, your security is roughly equivalent to the security of Ethereum.
So that's a really important property of this, in that if somebody submits an invalid transaction to the rollup cannot produce a proof that would convince the chain that the transaction is valid. Yeah, and this is backed by basically the math of the snark. Yeah, so when funds are stored in one of these rollups, there's really no way to kind of take the funds out without agreement of the fund owner. And again, this is backed by the security of the snark.
Yeah, I think that's one of the most beautiful aspects about this, is the fact that zkSync allows you to move a ton of the computation that would otherwise have to happen on mainnet off-chain, but they still inherit the security properties of the main chain by virtue of using zero-knowledge proofs. And so you have the same level of security that the layer 1 Ethereum blockchain has, but it allows you to perform the computation off-chain in a way that's much more performant and has higher throughput and lower latency, and addresses some of the limitations that Ethereum mainnet has without sacrificing security.
Precisely.
Dan, so I know you have a lot of questions and definitely want to allow you to jump in. So
yeah, actually, let me start with actually kind of a high level question. So suppose you have a high value asset. I don't know, you just bought your favorite CryptoPunk. What would you say? Would you rather store it on the Ethereum mainnet, or would you store it on a ZK Rollup, or which type of ZK Rollup? zkSync, ZK Porter. Could you say something about that?
That's a really good question. And this goes into risk assessment in general of all the blockchain protocols. So we have to be very clear here when we say that the protocol has the same security properties as Ethereum itself. We talk about the protocol itself. Every smart contract on Ethereum has some risk inherent to it because it's some code which can contain bugs. So like I would not trust a lot of my personal value in some new protocol immediately from the start. I would wait a little bit and give it some time and space to grow in value and see that nothing bad is happening. And after a year or half a year or a few months, the confidence will grow, because if there was any exploit in the contracts, it would have been already detected by someone and pointed out. So this security systems have this lindiness property. The longer they exist and the longer nothing bad happened, the more confident you can be about these protocols. But after a protocol have been time tested, I would totally trust a ZK Rollup with very high fortune, for sure. So you also mentioned a ZK Porter, and let me introduce this. This is an extremely exciting thing. Like it's an extension of a ZK Rollup, which is only possible with ZK Rollup family. There's another type of rollups called optimistic rollups. They unfortunately cannot do this. They do not rely on math and cryptography. They rely on game theory and validators, and they cannot have this extension. And so with zero-knowledge proofs, you could, in theory, rely just on the validity of these proofs and have the data be managed or be made available by some off-chain party, and such a system would be called Validium. So this third trusted party, like semi-trusted party, would not be able to do anything wrong with your transactions, to mess with the code of smart contracts and violate the rules, but they could theoretically make the state frozen, not provide the data availability. So if you trust them to not do this, you can use such a system. Otherwise, you are much better off with a rollup where data availability is solved on Ethereum. However, a rollup comes with a cost. Since we have to publish some data on Ethereum for every transaction, or for at least for every account which has been touched in this block, you have to pay to Ethereum validators, to the miners, for broadcasting this transaction, because you still need to make it available to everyone, to every full node on Ethereum. So it has roughly linear costs to the number of transactions in the block. And it roughly corresponds to, so it will grow linearly with the rising gas costs on the mainnet. So right now, the rollups we have for ZK rollups we have for payments are about 50 times cheaper than native payments on layer 1. And I expect that this ratio to remain roughly the same for also for smart contracts. So if you think that, like, if you have some complicated DeFi interaction and the Ethereum cost would be $1,000, then a rollup transaction would cost $20, but this might still be too high for a lot of people, right? So what they can do instead, they can rely on Validium, but in zkSync, this Validium system is called ZK Porter, because it actually, like, the data is not held by a centralized third party. It is still decentralized. We have a protocol which involves a group of validators called guardians who provide the security of this data using proof of stake delegation mechanism. The beauty of zkSync 2.0 is that ZK Rollup and ZK Porter can coexist in the same system, offering different accounts with different properties to users with different needs. Those who want to store highly valuable assets should prefer ZK Rollup. Those who need cheap transactions can go to ZK Porter, but they can still seamlessly interact with each other. So this is like having Uniswap on Ethereum and users on some side chain who prefer cheap transactions. Those users could interact with the same liquidity which you have on Ethereum seamlessly and atomically. This is very interesting.
I really like that distinction in that zkSync basically has kind of a bounded scalability factor over the layer 1 network because all the data has to be written to the layer 1 network. I think you mentioned it's a factor of 50 or so. Whereas ZK Porter seems like it could have an unbounded acceleration over the layer 1 network, right? Because now the data doesn't even live on the layer 1 network. So in principle, you can take as many transactions as you want and compress them into a short snark proof. And all the layer 1 does is just verify the short snark proof. So you have unbounded gas reduction using ZK Porter, whereas it's bounded improvements using zkSync. Is that a fair comparison?
This is a fair comparison, and the only thing which the users of ZK Porter have to take into account is diminished security, because we introduce a new security assumption, a honest majority or rational majority assumption for ZK Porter specifically. So theoretically, the guardians could freeze the data, but this would cost them a lot.
So your CryptoPunk, your expensive CryptoPunk, you would rather put that on zkSync than on ZK Porter.
The most expensive assets I would highly recommend to put on ZK Rollup. So you can think of it as savings account and current account. You probably have most of your money in the savings account, or in terms of blockchain, you can think of a cold storage. But then you have some smaller amount of funds that you use for daily transactions on a cheaper current account with cheaper transactions, lower fees.
Dan, do you want to briefly give some context around why the data has to be available? And that might help kind of inform the role of ZK Porter in the network.
Oh, for sure. Yeah, this is pretty important. I mean, so we're relying on sort of a validator to provide these proofs, and so the validator has to know the state of the world, how much is in everybody's account, and to make sure that other validators can come in case one validator goes down. They need to have access to all the transaction data that was made available up until this point. And so putting the transaction data on the layer 1 blockchain on Ethereum makes it possible for anyone to step up and act as a validator. Whereas if it's off chain, now we have to rely on in some sense the staked property of the other validators in order to for other validators to come online.
Yeah, exactly. Yeah, my intuition for this has been that, I mean, you could think of Ethereum as a computer, and it does two things. It can do two things. It can do computation, and it can also store data, but it's very expensive in both of those two things. And zkSync makes the data available, which, as Dan described, is important to be able to generate these zero-knowledge proofs by posting all of the data on Ethereum, and Ethereum then can make that data available to anyone who wants to generate the proof. ZK Porter is an alternative. Because Ethereum is so expensive, you can instead make the data available by putting it on ZK Porter, which is a side network that provides data availability, as a way of making it cheaper and more accessible to anyone who might want to generate the proof. But there are trade-offs, because you might think Ethereum is a more secure data availability layer than ZK Porter, which is why maybe for a very high value asset, you might want to go with a zkSync, whereas for a low value NFT, it's okay to go with a ZK Porter as an intuition for the trade-offs. Is that a fair kind of characterization?
Yeah, absolutely.
One of the things that may be interesting to discuss are kind of some of the trends around zero knowledge proofs. And I think in my mind, there are kind of three broad trends. One of them is the trend of the algorithms getting better. and allowing for people to generate zero-knowledge proofs more efficiently. Another trend, which I think is beginning now, is the trend of people building specialized hardware to generate proofs more efficiently. And both of these two things are on the kind of the proof generation side. And then on the other side, there's a trend on like programming languages. Like, how do you create programs that can leverage zero-knowledge proofs to be provable? And I think historically, like maybe Dan, I think you can share some of the history. I feel like there's a long history of verifiable computation as a subfield of computer science, and then all of a sudden it's begun to explode, in part because now there's a really key, like high value application for all of this stuff. And in the recent years, I think we've seen incredible developments on the algorithm front. We're now seeing kind of specialized hardware, as it's very clear that there's a lot of money to be made. And then I think also you guys, Alex, you're also innovating on the programming language side to make it more accessible for developers to write code for these things. So maybe Dan, if you could share a little bit about the history of the kind of the space and verifiable computation, and then Alex, would love to hear about what you're doing on the kind of the programming language side.
Actually, honestly, I think it's if I could ask like a question that would be more interesting to our technical listeners. Would you guys explain how you got the ZK EVM to work? I mean, compiling Uniswap v2 Solidity into a snark capable circuit. We thought this was going to be decades away, and you got it to work. Can you explain like what's the secret? What's the kind of the magic that made it possible for you to do this?
Sure, I can try to do this. So with zero-knowledge proofs, you have to perform a lot more computations than the naive execution of your code. So you have roughly a factor of 100 overhead on computation, like what your number of operations that your processor has to perform.
So maybe like Alex, if you'd like to talk a little bit about kind of the trends on programming languages for zero-knowledge proofs and how those things have evolved and what you're doing to make that friendlier, and how in the past it's actually been quite hard because the programming languages and tools haven't really been there, and they've only really kind of recently, and in large part because of the work that you're doing, have become a little bit friendlier. They're curious to hear about kind of the work you're doing on the ZK EVM. Like, what is the ZK EVM, and why do we need a compiler that's different from the compilers that exist already? And how does that make it easier for the developer to write code that ultimately leverages zero-knowledge proofs?
I have to begin by explaining how programs become zero-knowledge proofs in the first place. So unlike a normal CPU that executes transactions executes the operations one after another, to represent something as a zero-knowledge proof, you have to translate your program into a kind of arithmetic circuit, which looks very similar to a hardware circuit. You have some inputs, you have some gates that connect these inputs, and then you have some outputs. And you have to unroll the entire computation of your program into this one big long circuit. And unfortunately, in order to verify a zero-knowledge proof, you have to know exactly what the circuit is beforehand, in advance. So it made it very hard to turn zero-knowledge into something generic, because with custom smart contracts, you would need to deploy a lot of different verification keys for every smart contract on mainnet, on layer 1, which would be way too expensive and would defeat the whole purpose of scalability. So what we want is a single circuit that can verify any program. But how do you do it? Like programs that can vary in length, that can have conditional statements and so on, you can't really describe them as one single mathematical equation. So the trick that has been around quite some time that we are actually using is called TinyRAM. So we have one single universal circuit that can prove an execution trace of a program. So you don't have to to compile the program into a circuit. You have a normal virtual machine, but this virtual machine is structured in such a way that we can take a separate circuit and prove that we executed certain operations on certain steps. Just these operations have to be adjusted specifically to be efficient in this virtual machine. The problem is, with this approach, the overhead grows 1000x. It's very, very inefficient. It would be prohibitively expensive with regard to just hardware, but hardware computing capabilities, but also the cost to try to generate the proofs for a generic program with generic primitives like hashes and storage access and other heavy operations. So the trick that we used in ZK EVM to make the EVM compatible ZK Rollup possible was to separate the tiny RAM circuit, which is responsible only for the program logic, from the circuits which are optimized for doing heavy operations, which are not generic, they're rigid, and they're designed to just do certain type of hash, certain type of storage access, proving the Merkle paths to a Merkle tree. And then we combine all of them by means of recursion. And recursion is something that became available and became affordable on Ethereum just last year. Before that, it was very expensive. We had different proof systems that supported recursion, but they were way too expensive to be used on Ethereum. So this was the main trick that enabled us to build the EVM compatible virtual machine.
And why, can you explain a little bit about why it's important for it to be EVM compatible?
We actually started originally with building a custom language, which was optimized for zero-knowledge proofs. It was called zkSync. But we quickly realized that it will be really hard to onboard the existing ecosystem of Ethereum and let everyone rewrite their programs completely in this new language. And the problem was not the language itself so much, because we made zkSync based on Rust, and it was actually a simplified form of Rust. So like people would be able to learn it in just a few days, coming from Solidity background. The problem was with the tooling and the expertise available in the industry in general. So like you have a lot of code which is already battle tested, which has this lindiness property, which have been live on Ethereum for many years, and everyone knows that it's safe because it secures billions of dollars worth of value for such a long time, and it passes security audits. But most importantly, it's just been around for very long. And you want this code to be just seamlessly deployable. And then if you can do this, then everyone can do this, and you instantly have an ecosystem of other projects that are composable, that have APIs that your dApp can interact with, and so on. So we see it with alternative L1s. We have a couple of Ethereum killers having launched in the previous year with custom systems, with different virtual machines and different languages. And they didn't really get traction until they implemented Ethereum compatibility. And this is when a lot of projects started to go multi-chain and deploy, because all of a sudden the whole ecosystem could migrate together. And we realized that this is a very, very important property for Ethereum, for L2s in the first place.
Yeah, it's hugely important because it's easy to underestimate the network effects that a programming language and the set of tools around it have. And it's become very clear that Solidity and the EVM have kind of become the lingua franca of crypto and of Web3 so far. And it's an enormous cost for people to learn a new programming language and to learn a new tool chain, or to even build a tool chain if it doesn't yet exist. And so the ability to be able to port a contract or a program that's written in Solidity that exists and runs on Ethereum today without having to change it to zkSync, and to have it then benefit from zero-knowledge proofs is very, very powerful, and something that, as Dan was saying, people thought would be impossible. And so it's really cool that you guys have figured out a way of building a compiler that takes Solidity and compiles it down to a ZK circuit, such that it can be provable in the way that kind of ZK rollups allow. Would love to, I think in the last few minutes, we're almost at time, but we'd love to maybe touch on some of the applications that you guys are most excited about that people might build on top of zkSync.
I believe that most DeFi protocols from Ethereum will launch in zkSync actually from the beginning. We see a lot of adoption happening with other L2s and with alternative chains. So like every application that wants to go multi-chain will necessarily launch in zkSync. But I think that the most interesting things will arise from the ability of this chain to actually accommodate much larger user base and make a lot of transactions really cheap. So you can build stuff like social networks. You can build protocols that you like something we can't even imagine now, or we can't really predict, because this is going to be a trial and error process. But this is a case where quantity transforms into quality. By quantity, I mean the performance boost that the zero-knowledge proofs can provide.
Historical, that once you increase computing power by a factor of 10, you sort of get a whole bunch of applications you never even expected, you never even dreamed of. And probably, I think, Alex, this is what you're saying. The same thing is going to happen here, that, you know, we speed things up by a factor of 50, and all of a sudden we get a whole bunch of new applications we couldn't even imagine.
Yeah, absolutely. I love that. Cool. Well, I think that's a good time. It's a good way to wrap up. Thank you, guys. Thank you, Alex G, Alex V, and Dan. This was a super fun conversation.
Yeah, this was great. Thank you, Ali.
Thank you, Ali. Thank you, Dan.